All right, good afternoon and welcome to this week's Iowa Learning Farms Conservation Webinar. I'm Matt Helmers at Iowa State University, Director of the Iowa Nutrient Research Center and faculty affiliate with the Iowa Learning Farms. Iowa Learning Farms is a partnership of the Iowa Department of Agriculture and Land Stewardship, the Iowa DNR through Section 319 of the EPA, Iowa NRCS, and Iowa State University Extension and Outreach. And we feel very fortunate to be a part of Iowa Learning Farms and get to host. I feel fortunate to be a part of Iowa Learning Farms, get to host the webinars. And excited today to have our speaker. We have Marissa Osterloh, gosh, uh, that's a graduate research assistant in the Department of Agronomy. She's been doing some great work looking at modeling prairie systems. So her presentation is a modeling approach for quantifying the ecosystem services of managed prairie systems. As always, if you have questions, please type those in the chat box and we'll get those to Marissa at the end of the talk. With that, Marissa, the virtual floor is all yours.
Great. Thank you, Matt. So hello, everyone. As Matt said, I'm Marissa. So before we jump too far into my presentation today, I wanted to just take a moment and introduce myself. So again, I'm Marissa. I'm a graduate research assistant at Iowa State University. I recently actually just finished my master's and I'm now starting my PhD. But to take a step back, I'm originally from Ohio, so up here in the top left, that's Ohio, if you're not familiar with it. But right there where that little heart is where I'm from. I'm from London, which is a pretty small farming community, little town, and not many people live there, so everybody knows everyone. But growing up, I raised animals. I had cattle and goats and rabbits and just about everything in between. I showed in FFA and 4-H, and all of that kind of was my whole upbringing. But then I came to Iowa State in 2019 to start my undergrad. I actually came here as a meteorology student. But throughout my 4 years here, I continuously felt like the pull back to agriculture. So I was fortunate enough to land a master's appointmentship, I guess, here. I'm working with Dr. Andy Van Lukey and Dr. Fernando Miguez in the agricultural meteorology department. So that's kind of everything leading up until now. And we'll talk more about what I did during my master's, which is what my presentation has been on today. So to kick things off, I'm starting with some audience participation. So in the chat, if you wouldn't mind, if you're able to, I'd like you to type like one word or just like a little phrase about what comes to mind when you hear the word prairie. Is it agriculture, conservation, something else, flowers, whatever it be? Just go ahead and send that. I'll be able to see it come through. Great. I'm seeing some grazing, ecosystem, oh, bison, conservation diversity, awesome bees. Great. Wonderful. So I'm seeing a very general theme of conservation, grassland, stuff of along those lines, diversity, which are all really great things. So we're gonna kind of skip here. So this is how a prairie agroecosystem is defined. I've highlighted some keywords here, but this is just coming from Google. But it is a land management approach that incorporates prairie plant species into agricultural landscapes to enhance ecological sustainability. And I want that really to stand out to you, the enhanced ecological sustainability part. These systems really aim to mimic the structures and functions of natural prairies that once there were before. So I have a graphic here on the right that shows the historical range of tall grass prairie. And specifically, if you want to focus in on Iowa, Iowa used to be covered in 98% prairie. So today, less than 0.1% of that remains. But these prairie agroecosystems that are being implemented on land and landscapes across our state, but also across like the Corn Belt, are aiming to mimic these structures that once here were here before. But while also, most importantly, and I probably should have highlighted that, is while supporting agriculture production. So we're not aiming to remove all farmland. We're also aiming to support agricultural production using these systems. And ways that they do that is by improving soil health, reducing nitrate leaching, and increasing biodiversity, like many of you said in the comments of diversity, and then also helping with carbon sequestration. So, to kind of pull things out from this blurb of text that I have here, I highlighted those. We're going to kind of zoom in on that last part that talks about the different potential benefits of a prairie agroecosystem, specifically in regards to agriculture within that same realm. So first, we're going to focus a little bit on the ecosystem part. Several people in the chat said bees, which I was super excited to hear about, or flowers, or native, things like that. That is one of the best benefits of a prairie agroecosystem is its increased diversity being restored back on the landscape, specifically in terms of plants and animals. So bringing back species that were here once before, hundreds and hundreds and hundreds of years ago, bringing those back onto the landscape where they used to be. Another like overarching benefit would be the environmental benefits, and I have several here listed, which would be reduced nitrate leaching. And I think something that you can pull from this graphic here is the differencing in root structures between a prairie system here on the left. Hopefully you can see my cursor. And then also from a traditional annual system like corn on the right. The differences in rooting structure can really help bring the point home about nitrate leaching. The longer rooting structures you have not only keeps the soil where it needs to be, not eroding away, but also allows for higher nitrogen retention in the soil, being allowed for nitrate to be taken up because the roots are able to extend longer. So there's less nitrate escaping to waterways. With that, there's also been some studies that have suggested that because, again, of this high below ground biomass that's sitting in the soil year round, it improves soil organic matter and also reduces greenhouse gas emissions. On the flip side, so the left side of the screen where I had those benefits were stuff that's really been studied well and in depth in the past, specifically related to the prairie aspect. But if we want to focus in on the economic aspect, maybe something that's not been in-depthly explored before is related to the cellulosic biomass production. So prairies, we grow them, obviously, and what we're trying to do is produce enough biomass that could potentially be used as some sort of like energy input. So using these biomass in perhaps anaerobic digesters or something else that can produce energy that would be relatively carbon neutral. Um, the other idea, and again, someone else mentioned this in the chat, is it's highly productive. So we could use this for grazing on a flip side of perhaps a corn soy rotation, but maybe for like a cow calf production, we could use prairies for a grazing standpoint. And then also the prairies could be harvested and used as an alternative for animal bedding, perhaps for poultry or other livestock as well. So that's kind of just an over encompassing look at all of the potential benefits that these agroecosystems have to offer. Now what we're really going to do is focus in on the two that I have highlighted here in red, which are the reduced nitrate leaching and also in the economic side, the cellulosic biomass production. So this kind of also leads to our problem. So what I mentioned here is reduced nitrate leaching and the cellulosic biomass, but this also leads to our problem. So those are benefits, but we're seeing that prairie adoption across specifically the Midwest and Iowa, the on marginal land is sparse, and that's due to economic trade-offs. And what I mean by that is that it's well known that placing a prairie on agricultural land, perhaps where corn and soybean are, would not be as profitable as your traditional annual system, unless that is marginal land that is already not profitable to begin with. And I kind of have a graphic here on the right, this top right graph, kind of showing that. So perhaps in these green areas in the field where we're having positive profit from a soybean production would not be the most beneficial place to put a prairie because it wouldn't be economically sustainable. But in areas where we're already losing a lot of money, especially like in potholes, like what we're seeing down here in the satellite imagery, might be good places to put prairies. But that's still not being adopted due to the lack of market for prairies. So we're not really seeing prairie production because there's no place for farmers to sell it, right? So why grow it if you can't sell it and make a profit? Secondly, is the need for ecosystem service payments. So I mentioned nitrate leaching and greenhouse gas emissions. All of those are really wonderful things that we as individuals would like to see reduced, but that benefit perhaps isn't outweighing the cost, right? So if we're not getting paid for those benefits, again, it might not be economically feasible to do. And the last, I touched on this a little with the cellulosic biomass, would be the anaerobic digestion. So promoting that more so that we're all aware that that's something prairies could be grown for is to produce renewable natural gas using anaerobic digestion. So that leads to our goal is not only just to highlight what prairies can do and what they offer in terms of their benefits, but we are also aiming to build a model that has high accuracy using a test site here at Iowa State. So we're developing this model using a test site to calibrate it to show above ground biomass production, nitrate leaching, leaf area index, and drainage. Today, we're really going to focus in on the above ground biomass and nitrate leaching aspect of that, but we did use the other ones. And more explicitly, we're aiming to demonstrate that this model can predict these variables, so above ground biomass and nitrate leaching, not only at a calibrated site, but at other sites across the country to hopefully help develop a market in the long term for these systems. So moving into how we did this, so we used the comparison of biofuel cropping systems, COBS, here at Iowa State University, that's just south of Ames. It's a 24 plot experiment, each being about 27 by 61 meters in length and width. And each block, that's what this drone imagery is showing, by the way. Each block has 4 replicates of each system, and each system is a continuous corn treatment, continuous corn with a cover crop, which is winter rye, a corn soy rotation, and then also a fertilized and unfertilized prairie system. And in each of those parentheses there on the screen, you can see the different nitrogen application rates. And one thing I want to point out is that the fertilized prairie is receiving about half of what the continuous corn or corn soy rotation is receiving. To focus in on the prairie, since that was really what we were concerned about at this site, the prairie was fertilized roughly every April, give or take. And then the prairie was mowed and baled roughly every late October, early November to mid-November at the latest. So that was the site in itself and how it was managed. Different aspects that we're using for the calibration of the site is the biomass data. So specifically the above ground biomass and when it was dried. Leaching, and again, we're specifically looking at the nitrate leaching and we're getting that. So this site is tile drained. So we're getting that from these drainage pits that's kind of shown down there in that picture. I took LAI data in the 2024 growing season to, if you're not familiar what LAI is, it's leaf area index, and it kind of shows the light at the top of the canopy versus at the bottom of the canopy. So it tells us about basically how much the prairie is growing throughout the growing season. So it gives us an insight on like the productivity throughout the growing season. So we used that as well to kind of calibrate the model. We use species diversity, which really just looks at how many species are growing within inside each block of each prairie system. And then also the nutrient content. That picture there is the nutrient content of the plants, but we also focused on the nutrient content of the soil as well. So that was our calibration site. I also mentioned in our goal that we were looking to test the model after we calibrated it at different sites across the country to show its validity. We used 2 different sites, one in Kansas, which is the Konza Prairie Biological Research Station, and then also one in Minnesota, which is the Rosemount Research and Outreach Center. Um, to focus on the one in Minnesota first, it was established in 2004, but the prairie itself wasn't established until 2015. It was an unfertilized prairie and it was harvested every year between 2015 and 2019. I also want to mention that that site, we don't really have a lot of information about its management practices other than what I have told you here. Getting a model to kind of respond to that was a little challenging given the lack of management history that is known. For the one in Kansas, the Konza Prairie, it was originally established in 1977 with 7,700 acres of prairie. And then data collected for what we used for this study, it was from 1984 to 1990. It was also an unfertilized prairie. And something specific about this site was compared to Cobb's in the Rosemount Research Center, where we only had harvest biomass measurements. At the Konza Prairie, we did have interannual measurements of biomass about 12 to 15 times throughout the growing season. I'll talk about that more and show you that in a minute. So to kind of walk through our methodology, we are using APSIM, which is the Agricultural Production System Simulator. Um, it's a model that simulates it's a virtual farming model that simulates corn, soybean. It also has a perennial pasture model, which is what we planned on using, which is the ag pasture model to simulate our prairie. So we're using that, and specifically on the left here, what I have displayed is the inputs that's required by that model. So we need to know management history, such as planting date, fertilization, and harvest. The weather data, what crops you're using. For us, that would be a C3, C4, and legume, since that's primarily what prairies are comprised of. And then also the soil data, so things like the percent sand, silt, and clay, the pH, and the bulk density. For the weather and soil data, we are getting those respectively from NASA Power and the National Weather Service co-op stations, and then also from Surgo, and then also soil samples that were taken at the field site itself. Those soil samples were taken in 2008, so Surgo was really to supplement those and update those accordingly. So, like I said, we're using AppSim. Again, it's a virtual farming simulation that's able to produce different outputs. But something specifically that we're doing, so the ag pasture model itself aims to simulate a competition between the C4, C3, and legume species. Instead of simulating a competition where we found some errors in terms of output, we instead split up the simulations. So each simulation would have its own grass type, and then we would average them together after the fact, based off of the species composition that was collected at Cobb's that I mentioned a minute ago. So this was the main difference between the fertilized and unfertilized model outside of fertilization itself. So, for example, for a fertilized prairie system, we would run the model and then multiply the C4 simulation by 69%, the C3 simulation by 30%, and then the legume by 1%, since that was the species composition, to get our whole prairie and sum them together. Outputs that we were really concerned about specifically was greenhouse gas emissions, the above ground biomass production, and then also, like I mentioned, drainage and leaching. So I wanted to give you some snapshots of what the model actually looks like. So this is kind of a screenshot of what the APSIM framework looks like. So we have simulations set up here of ryegrass, red clover, and Rhodes, which is the C3 legume and C4 grass. And that is all within like one model itself, but they all have separate simulations. A look inside of what one of the simulations would look like. So specifically here, this was ryegrass, but they're all the same. Is we would have our weather data, our field, which is comprising like of our soil data, and fertilizer schedules. So when you apply fertilizer and things like that. So this is kind of looking inside the weather folder inside the model. So the model itself requires information about maximum and minimum temperature, precipitation, and then also radiation. So we generated this weather file using NASA Power and imported it into the model. And then lastly, I wanted to show you how we were harvesting this prairie. So the way that the ag pasture model is set up is by using a simple grazer. So basically using cattle to eat the biomass. But we were able to set that up to mimic how a harvester would do that. So we would only allow basically the cattle into the field one day out of the year, which would correspond to the harvesting date, and then record the biomass that way. So within that model, there are different parameters that you can refine. So such as the photosynthetic rate, so how fast basically the plants can grow, the maximum potential rooting depth, so how far the roots can go within the soil, and then also the nitrogen concentration optimum of the leaf, which is the nitrogen that is in a leaf, the concentration of that that would be optimal for plant growth. So there are maximum and minimum, but here we were really concerned about the optimums because that would lead to the most amount of growth. And then the maximum and minimum in fixation. We change these parameters based off of an optimizer and also based off of literature. These four parameters were given to us via a sensitivity analysis that we did of the model, but I'm not really going to get into that. If you have questions about that, I'm happy to explain after. So this is an example of how we're quantifying the model. So you're going to see throughout the remainder of the presentation the RMSE of the model versus the RMSE of the mean. And this is really an example of how we are going to go about that. So I told you that I'm a meteorologist by trade. So this is a good way to kind of do that is via weather forecasting, since you're all fairly familiar with that if you watch the news or just look at your phone in general. If we take average maximum and minimum temperatures in Ames for May, which would be 62 degrees Fahrenheit and 38 degrees Fahrenheit, that would be corresponding to the RMSE mean. So that's your mean or the climatology of weather in this case. But we do have a model for weather or just forecasters at the National Weather Service office that are giving us predictions of what they think the high and low temperatures are for any given day throughout the week, which is really what I've given you here. This is an example of 3 days. Below, I've given you what the actual temperature, though, of that day was for the maximum and minimum, and then also the difference between if we just use the mean as a predictor versus if we used what the forecast was. These red, the numbers in red show that the mean did worse versus if it was in green, the forecast did better. So for Friday and Saturday, for the high and the low, the forecast was much better than just using the mean, saying it was going to be 62 today, but in reality it was 76. That was worse than saying, well, actually, or sorry, it was actually 78, but instead the forecaster said it was going to be 76. So that's kind of an example of a model versus a mean and how we're going. What we want is that the model to do better than the mean more often than not. Because if you were able to just always say that it was going to be 62 today, because that's what the average was, you wouldn't need a model or someone telling you what the weather was going to be that day. So that's kind of what we're doing, but in the essence of prairie production. So just to recap really fast, what we've done is we've created a model and calibrated it based off of Cobb's observation data. We're evaluating the model based off of the root mean square error, like I just mentioned, about which one is going to do better at predicting what actually happens. And then lastly, we're going to test it at different field sites throughout the United States. So here I'm showing you a result of the above ground biomass, and I'm not going to spend a whole lot of time on this graph particularly, but I do want to point out that the root mean square error here for both the model, which is going to be at the top, and the mean that's going to be at the bottom of the graph, for both the fertilized and unfertilized model, we see that the root mean square error of the model is less than the mean. Again, showing that our model has higher accuracy than just using the mean of the observations. So more importantly, though, I think it's important to look at the mean of the model outputs. So the top is just going to be the unfertilized prairie versus the bottom, which is the fertilized prairie. And Importantly, I think that the model does a really great job at capturing the mean of biomass production, especially for the fertilized prairie. It does a good job also at showing the difference in the observations. So, something to take away here, and you can see this in the pictures that I supplied here, but the fertilized prairie has about double what the unfertilized prairie does have in terms of above ground biomass. And the model captures that pretty accurately on average throughout the entire time period that we're looking at. Again, this shows that we have fairly good promise in the model if it's able to capture this. Looking at nitrate leaching, this was something that was fairly hard for us to quantify using the model. Um, as you can see here, the RMSE of the model is larger than the RMSE of the mean, showing that if we just use the average, we'd actually probably do a much better job at guessing year to year what the nitrate leaching is. And that's because the nitrate leaching variability between year to year is really, really small. And I think that's an important takeaway. We see that basically every year we have less than 1 kilogram per hectare of nitrate leaching, which is phenomenal in terms of both from a fertilized system and from an unfertilized system in terms of nitrogen retention. To take a look at this maybe more in a context that maybe you're a little bit more familiar with is in terms of nitrate leaching reduction. So what I'm showing here at the top part, the first two bars would be the reduction if you had a soybean system and turned it into a prairie system versus if you had a corn system and turned it into a fertilized prairie system. And the model is able to capture the reductions very well. So showing that if we turned a soybean into a unfertilized prairie, we would have on average about 15 kilograms per hectare nitrate leaching reduction. And then for a maize, it would be about 16 kilograms per hectare. That's really good. And this shows that our model is really picking up on the difference between an annual system and a perennial system, and really also showing the differences probably in root structure if it's able to show this difference in nitrate leaching that I've shown here on the left via these pictures. So the differences in the basically the extension of the root throughout the soil profile. So moving into the test sites, so just to recap from the calibration, what we were able to see is that the model does a fairly good job at predicting above ground biomass and then reductions in nitrate leaching. So we're going to try to do the same thing at sites that the model doesn't really know anything about or that wasn't calibrated to. We only have data though for above ground biomass, so that's really what I'm going to show. So focusing on the Konza Prairie Biological Research Station that's in Kansas, again, like I said, this one has 12 to 15 observations per year. We do a really good job at this one at guessing biomass throughout the growing season, not just at the harvest, which is again showing really good validation that the model is able to capture prairie growth throughout the season. We see that the RMSE of the model is again less than the RMSE of the mean, showing that we have higher accuracy than just using the mean of the observations as a predictor. And then secondly, we looked at the one in Minnesota, which is the Rosemount Research and Outreach Center. And this one, like I said, we had few data samples, so we only had 2015 to 2018. And then there was unknown management, which led to a lot of uncertainty through the model. So what we did here was we used Cobb's composition since we didn't know the composition of the prairie at all, which is going to be the black circular point. And then we also tried running the model with different compositions, just guessing. So using a C3 composition, which was 100% C3, and then also a C4 composition. I think even though we were never able to get an RMSE that was less than the RMSE mean, I think what this graph really shows is how sensitive the model is to the species composition. Knowing that is a really big factor in the model performance. So that is something that would need to be improved upon going forward, is knowing that species composition. So just a quick summary here of my results. The model has higher accuracy at predicting the average of investigated variables than just using the mean of the observation, which was our primary goal, was being able to just do better than using the average of something. And then the model can predict above ground biomass at an unparameterized field site with mixed accuracy. And the main limitation of that is, again, lack of knowledge about the management and also the prairie species composition. So knowing what the actual diversity is going to be a challenge moving forward. So, some future work. So I mentioned a lot at the beginning of this is that we want to implement these systems where perhaps row crops are not profitable, to not take away from row crop production where it is profitable. So if we can place these systems where there are potholes or constant flooding, like I have in these pictures here, um, where perhaps a perennial system would do better at producing biomass than a corn or soybean based off of yield monitor data, that would be a good spot and a good indicator of where to put these systems. So that way that there would be enhanced economic sustainability for a farmer moving forward. Um, there needs to be a lot more work done with this in terms of getting yield monitor data and identifying areas where there's consistently negative yield from a corn system that would identify a highly unstable area where we could place these systems. But this is a really big prospect of future work, especially for me moving forward, that I'm really interested in. And if you have questions or thoughts about that, I would love to hear that as well. I'm just going to leave you here with my conclusions and contact information. Um, just summarizing again everything that I said, and I'm happy to take any questions. So thank you.
All right, thanks, Marissa. Maybe we'll get through the Iowa Learning Farms logistical slides there. If you are on today and watched live and want to earn a CCA CEU, please send your name, the name you entered to watch the webinar, and your CCA number to Elena Whitaker, ALENAW at iastate.edu by 5 o'clock today. Again, include your name, the name you entered to watch the webinar, and your CCA number. Let's go to the next slide. Okay, if you watch this webinar live and are willing to fill out a voluntary demographic survey, we would greatly appreciate it. Only one response is needed for all 2025 webinars, and you can either scan the QR code or go to that website address there, iowalearningfarms.org/survey. Thank you very much if you've done that, and if you're willing to do it, we greatly appreciate it. Next slide, we'll put a plug in for, all right, we got Celeste Sigdahl, that's a PhD candidate at Penn State, is going to talk about improving manure and nitrogen management in no-till dairy cropping systems. So if you're interested in manure and management, please tune in. And then one last slide here is if this webinar will be archived as are all previous webinars, and you can find those on the Iowa Learning Farms website or at the YouTube page, Iowa Learning Farms dash webinars. Okay, we did get some questions here, Marissa, and maybe to start with, what do the C3 and C4 designations mean?
Yeah, so those are different photosynthetic pathways. So C4 is going to be a warm season grass. So if to put this in context, maybe of row crops, that's going to be the same thing as corn. So warm season, they're going to have peak basically growth in warmer season months. So typically in like July and later. C3, though, is going to be your cool season grasses. So perhaps a lot of maybe what's growing in like your flower beds and things right now. Things that are going to grow in much cooler temperatures. So have peak growth usually around now, actually. So May and June. So.
And then does the balance of C3 versus C4 versus legumes tell us anything about the health of the prairie ecosystems?
Yeah, so not necessarily health, I would say. That's a really, really great question. Um, because different prairies can have different compositions and it doesn't make one more healthy or not. all it really tells us is perhaps what was planted originally, and then also the competition of the prairie if you knew what was planted originally. So that can also tell you a little bit about management and things of that nature. Usually you end up with C4 dominating a fertilized prairie just based off of nitrogen alone, and then a C3 in an unfertilized because there's more of a nitrogen limitation, if that
Yep.
makes sense.
Yep. Uh, and this one, when was the prairie established?
Yeah. Um, it's a really great question, and I probably should have said that. For the Cobb's parameterized field site, that was going to be in 2008. And then for my test sites, for the one in Minnesota, that was in 2015. And then in the one in Kansas was in 1977. So, and that's still an established prairie today. So.
Yep. And this person indicated or asked a question that this was just for the prairie systems at Cobb's, I believe that is, there was just a harvest once per year.
Correct. Yep.
Yep.
Just
And
once.
it was at the um, end of this season. I think you said in November.
Yeah, on average, it was in November. Yep.
Yep. Ah, did you, that's a good, kind of a good question. Did you look at the difference is in the water balance under the different land covers?
Yes,
Okay.
loosely. So I did look at so I looked at the water balance, and specifically I looked at evapotranspiration and drainage, runoff, um, and things of that nature. So basically, we didn't spend a whole lot of time on that because we don't have ground truth data except for drainage. But we are looking at evapotranspiration because I do think that there may be something wrong with the modeled water balance, which is leading to some issues with my drainage that I didn't show here today. But um, if you're interested, you can look at my thesis
Yeah.
online.
Yeah. Okay.
So, but there is some issues I think with the drainage part of this, and I see that it's Antonio that asked this. So
Yeah.
I'm happy to send you an email about this to follow up. But we think that there's something wrong with evapotranspiration in short. So we're going to look at some stuff from the energy farm in Illinois that does have evapotranspiration data to kind of see if we are even close at evapotranspiration values from what we're modeling. So
Um, and this one, I guess, yeah, there were some questions about prairie establishment, and it was kind of established with common procedures. And so this was, we're pretty lucky, I think, at this site with how well it performed. And um, oh, there's a question about numbers and diversity of wildlife. I guess at this site, I don't think we've really done um, wildlife measurements. There's been some work looking at vegetation diversity and so forth, but not necessarily wildlife. And then I guess this would, yeah, for you, Marissa, in the future, does your model take into account till versus no-till row crop practices?
it it does. Yes. That's not necessarily something I spend a lot of time looking at, but
Yeah.
yes, it does.
Yeah. Okay. And this, I think you may have said it, but at the Cobb site, we are in a no-till cropping system. So in this case, it wasn't like any of the nitrate leaching differences were because of tillage versus no-till in the prairie, even though we don't expect tillage to have a big difference. But yeah, I think that gets most of our questions here. There was a question about I think the N leaching, and this was on university land and then drained into a drainage main. Um, we got the when the prairie was established. So, Marissa, thank you so much for this great work. I think one thing is you may be underselling how much work was done to get this model to work for prairie. So, I think this is a huge accomplishment and has huge implications as you start to look at trying to model some of the aspects you talked about into the future. So, I think that this really beneficial. I'd encourage people, if you have additional questions for Marissa, please email her, and her contact information is below. As always, if you need a CCA CEU, please email Elena Whitaker at alenaw@iastate.edu by 5 o'clock today with your name, the name you entered to watch the webinar, and your CCA number. And please tune in next week for Celeste talking about manure, nitrogen, and availability. So thanks again, Marissa.
Yes, thank you.